Perhaps the best way to introduce this video is with this computer-generated diagram. There's quite a few things going on, but I'll describe what we're looking at. What we are watching is as the red arm that extends from the origin to the edge of the circle. The orange line is a line tangent to the circle where it meets the x-axis. The yellow line extends the red line out to the orange. The blue arc is the arc length between the red line and the x-axis, and the green line, as we recounted, is the height of the red line when it intersects with the circle. Whew, that was a lot of describing. For the most part, I want you to pay attention to the length of the green line, the length of the blue arc, and the length of the orange line beneath the yellow line. So, not the entire thing, just below the yellow line. Let's watch as the angle decreases. One more time, but at half speed, just so we're entirely clear that the lengths of these three lines is becoming equal, but the green is always the shortest, and the orange is always the longest. With this concept in our head, this looks very similar to a squeeze theorem problem. So let's see what limit we can generate from this phenomenon. The first thing we will want to do is label the red length as 1. And remember, geometry is scalable, so this will visually yield the same result at any scaling of the length of the red line. With the scaling down, the angle that is made between the red and the x-axis can be called x, since we're going to be making this into calculus and not geometry where we'd normally use something like theta. Next, we can easily notice that the green line is just sine of x, as it was defined in the trig series. Sine of x is just the height. Following more of the reasoning that was laid out in that trig series, if the radius is 1, then if we're using radians, the arc length is simply the measure of the angle, or x. So when we were at pi radians, it was half the circle, which is distance of pi. Half pi radians, well, that's a quarter of the circle, which is distance half pi. Radians equals length for radius 1. Now, for the orange, which is more complex. The x-axis is normally cos of x, but it is scaled up to a value of 1. Here's an animation that shows that these two triangles are similar, as one slides easily into the other. This means that if cos x is scaled into 1, then everything must be divided by cos x, since cos x over cos x is 1. Well, if the green, which is sine x, scales into the orange, then we must divide sine x by cos x, which can easily be translated into tan x using the tangent identity. Now, we can confidently write out our inequality that is valid between pi over 2 and 0. This gives sine of x less than or equal to x less than or equal to tan x. Pretty useless limit so far, as if we took the limit as everything approached 0. Everything here approaches 0 no problem. But if we divide everything through by sine x, we obtain 1 less than or equal to x over sine x less than or equal to tan x over sine x. As we know, there's a sine x on top of the tan x, so we could cancel those out to yield 1 over cos x on the right. The next thing we will do is flip the term so that cos x term is on top. And we will also have to flip our inequalities, as if we said 1 is less than 2, we better not say 1 is less than 1/2. We flip it. 1 is greater than 1/2. This gives us our final and interesting inequality of 1 less than or equal to sine x over x less than or equal to cos x. Now we can take our limit as everything approaches 0. Now guaranteed that we will squeeze this new limit that we've never evaluated before. Taking the limit on the left will simply yield 1 as nothing changes, and on the right it will also approach 1 since cos of 0 is 1. This clearly leaves the final statement that the limit as x approaches 0 of sine x over x equals 1. With this limit now defined, we are free to start taking the derivative of trig functions. Until next time, keep on learning.